This problem says two cards are drawn with replacement, and that phrase is so important that I underlined it. Two cards are drawn with replacement from a deck of cards and the number of black cards is noted. If X is the random variable representing the number of black cards drawn, construct the PDF, the probability density function. I'm going to solve this problem without using any special counting techniques and use only the things that we've already done. In particular, I like to use tree diagrams to generate these sample spaces. So I'm going to use B for black and R for red. So on the first draw, the card could either be black or red. If the first card is black, the second card drawn could either be black or red. If the first card drawn is a red, the second card drawn could be either a black or a red. So this is going to allow us to find our sample space. And in particular, I can see that going down this branch produces a black followed by another black, which I'll write as BB. Going down this branch produces a black followed by a red, which I'll call BR. Going down this branch produces a red, then a black. And going down this branch produces a red and another red. So that generates our sample space for us. Now we need to use our knowledge of a deck of cards. We know there are 56 cards and half of them are black and half of them are red. In other words, 26 red, 26 black. So the probability of getting a red randomly drawn or the probability of getting a black is 1/2. So what I would do is take the probability of getting a black and put it actually on the branch itself. Every time you see a B branch, put 1/2. And since the probability of getting a red is also 1/2, on the red branches I'd also put a 1/2. And that allows me to sort of see the probabilities of going down each branch. Of course, the reason I'm doing this is I want to find the probability of going down each branch. I want to find the probability of getting two black cards, a black followed by a red followed by a black, and a red followed by a red. And I know from our past experience that if I use the multiplication principle visually, I'm multiplying down a branch, and that's a visualization of the multiplication principle. So the probability of getting a black followed by a black is simply 1/2 times 1/2, or 1/4. And using that same logic, I can say the probability of getting a black followed by a red is 1/2 times 1/2, which is a 1/4, and the probability of having a red followed by a black is 1/2 times 1/2, which is a 1/4, and the probability of having a red followed by another red is 1/2 times 1/2, which is again 1/4. And from here, of course, I could just write out the sample space. You've got BB, BR, RB, and RR, and I'm actually going to put those probabilities just above each element of the sample space just to emphasize the fact that those probabilities have already been calculated. And just to remind ourselves, I'm going to actually write this down again, that X represents the number of black cards drawn. So the probabilities that I need for my PDF are the probabilities for every possible value of X. So I could have no black cards, and the only way that can happen in this sample space is if I get two R's, and the probability of that I can read right off of here is 1/4. And using similar logic, I want to know the probability that X is equal to 1. That means the probability that I get exactly one black card. Well, that will only happen if the first one's black and the second one is red, or the first one's red and the second one's black. Well, the probability that the first one's black and the second one red is 1/4. You can look right here. And the probability that the first one's red and the second one is black is also 1/4. So the probability is 1/4 plus 1/4, which is 2/4, and of course that reduces to 1/2. And finally, we play that same game, or use that same strategy with X equal 2. That's the probability that we get two blacks. The only way you can get that, looking at the sample space, is if we get both B's, and the probability of that is 1/4. So now it's a simple matter to get the PDF. A PDF is just a listing of every possible outcome. The values of X could either be 0, 1, or 2. You're only drawing two cards, so you could at most get two black cards. You could have one, or you could have none. And we've just calculated the associated probabilities. The PDF is a listing of every possible outcome along with their associated probabilities. So this table represents the PDF, the probability density function that we were looking for. I do want to mention one other thing about this problem, and that is if you were really understanding what's going on here, you probably realize that I did a lot of work that probably didn't need to do. And that's why I propose this alternate solution for those that really understand what's going on here, because if you're not sure, that solution method that I just went through is probably the best way to solve this problem. But if you can think this through, this is going to be faster. So if I go back, I want to propose this alternate solution. This alternate solution depends on understanding this idea. If we can be absolutely confident that we're working with an equally likely sample space, then we can avoid having to use the probabilities on those branches and instead just use the tree diagram to generate the equally likely sample space. So, whereas before I went in and generated these probabilities, if I can convince myself, because they're the same number of black cards as there are red cards and I'm drawing with replacement, that the probabilities are all going to be the same, that's going to generate an equally likely sample space. So it's just as likely that I'm going to get two blacks as a black followed by a red, or a red followed by a black, or a red followed by another red. Those are equally likely. I know that because I've already calculated the probabilities, but if I can convince myself that this sample space is going to be equally likely without even calculating the probabilities, then I could just dispense with this. I could just not ever calculate these and just use the tree diagram to generate the equally likely sample space. So I would just use the tree diagram to say, well, I've got BB, I've got BR, I've got RB, and I've got RR, but I'm not even going to generate, I never even, using this alternate solution, I never even generated these probabilities on the branches, because if I'm confident that they're equally likely, I don't really need them. What I just said is so important, I want to actually let you look at it in writing and think about it. What I just said is, as long as we know we have an equally likely sample space, we don't actually need those branch probabilities that we calculated in the alternate solution method. Instead, all we need is just identify the number of black cards in each of the equally likely elements, and there are 4 of them in this problem. We don't really need those individual branch probabilities if we know for certain that the sample space is equally likely. And instead, all we need to do is identify how many black cards each of these represents. BB represents 2 black cards, BR represents 1, RB represents 1 black card, RR represents no black cards. And then you can see the probabilities are going to be easy to calculate. The probability that you don't have any black cards, that's just a 0 black card, there's only 1 of them, so it's going to be 1 out of 4. The probability you have exactly 1 black card, will count the ones. You've got 1, 2, 2 out of 4 is 1/2, and then count the 2s. There's only 1, 2, 1 out of 4, and you get exactly the same answer we got earlier. So the idea here is, if you can absolutely be certain that you're working with an equally likely sample space, you don't really have to do the branch probabilities. But if there's any doubt at all that you're working with an equally likely sample space, you need to back off of this alternate solution and go back to the first way we did it. In any case, what you end up with is exactly the same sample space we got in the original solution. So you can solve the problem either way in this particular case, but it only works both ways because we have equally likely sample space, and that does not always happen. So the first solution is the safest way if you're not sure. If you're confident you've got an equally likely sample space, the alternate solution is faster and easier.